All right, so we have seen basic definitions. We continue with blocks. And we start with cryptographic hash functions and how they are used in blocks. So we already know what a cryptographic hash function is and how they are used, but in blockchains, they are used for many purposes. So within a blockchain network, cryptographic hash functions are used for many tasks, such as address derivation, creating unique identifiers, securing the block data. A publishing node will hash the block data, creating a digest that will be stored within the block header. Securing the block header, a publishing node will hash the block header and it will be included in the next block header. So this is how you link it. So hash functions are used for these purposes. So let's look at what are actually stored in blocks and what they are. Each block in a blockchain can contain 0 or more transactions. This is important. Most of the alternative cryptocurrencies have 0 transactions most of the time. You might think that why this is right. If there are no transactions, why I'm constantly writing blocks? We said that, in Bitcoin, in every 10 minutes, we are writing blocks, right? Actually, in those blocks, we are storing all of the transactions we hear, right? So what happens if we don't hear any transactions? So you might think that we can just wait, right, to hear more transactions. But if you do it, somebody can go back, modify previous blocks, and then add more blocks to it and create a blockchain that is longer than yours, which eventually become the original blockchain. So in order to avoid this kind of attacks, even if you don't hear any transactions, you have to constantly write it. Okay, this is valid for permissionless blockchains. You don't have to do that in permission blockchains. Okay, so this is why in every 10 minutes we are trying to write Bitcoin blocks, regardless of how many transactions you hear. So in an alternative currency, if the block writing period is 1 minute, this means that you are adding a block every 1 minute, even if they don't have any transactions. But of course, the miner gets rewards anyway. So it contains actually a single transaction, which the miner awards themselves. Okay. So we will go back to it when we talk about mining at the end. Okay. For some blockchain implementations, a constant supply of new blocks, even with 0 transactions, is critical to maintain the security of the blockchain network, which is what I mentioned just right now. Yeah. By having a constant supply of new blocks being published, it prevents malicious users from ever catching up and manufacturing a longer altered blockchain. The data which comprise the transaction can be different for every blockchain implementation. However, the mechanisms for transacting is largely the same. You sign the transaction, that's it. But what happens in the transaction actually determined by the blockchain implementation. In cryptocurrencies, most of the time, you are transferring some cryptocurrency from your accounts to some other accounts. A user sends information to the blockchain network. So whenever you want to make a transaction, you actually announce it to the network. Okay? The information sent may include the sender's address, sender's public key, a digital signature, transaction inputs, and transaction outputs. Okay, this is actually what we do in cryptocurrencies most of the time. While primarily used to transfer digital assets, transactions can be more generally used to transfer data. And later on, we will talk about pay-to-script hash in Bitcoin and also smart contracts. You will there realize that you can actually transfer something more. In a simple case, someone may simply want to permanently and publicly post data on the blockchain. So this is why actually you hid some information in the blockchain. We will see some examples. For instance, in Bitcoin blockchain, there are many hidden messages written by the people who make transactions. Sometimes people, propose to some people and that kind of stuff. So we will see some examples and I will show you how you can find them in a Bitcoin blockchain. In the case of smart contract systems, transactions can be used to send data, process that data, and store some results on the blockchain. Okay, so smart contract actually defined differently in different blockchains. For instance, in Bitcoin, we also have smart contracts, but there when we say smart contract, we are actually thinking about a contract that is digital, okay? So for instance, you want to sell somebody a house and you want to create a transaction about it, But in order to do that, you physically give the house and then you write it on the blockchain somehow, right? So this is also considered as a smart contract. But for people who born with Ethereum, their smart contract is just a programming code. So instead of writing a transaction on the blockchain, you write a smart contract there, which is actual piece of programming code. So anybody can, run that code in the future. So that kind of smart contract idea is different than the smart contract idea in the Bitcoin, okay? So definitions are completely different. So whenever somebody says there are no smart contracts in Bitcoin, they are right and wrong, because it depends on how you define a smart contract, okay? But if you think about like in the Ethereum case, where you have a programming code, you write it to the blockchain, Bitcoin doesn't work like that. That we will explain it more in detail when we talk how Bitcoin works and how it is different than Ethereum and so on. For example, a transaction can be used to change an attribute of a digitized asset, such as the location of a shipment within a blockchain technology-based supply chain system. So as you can see, you don't need to transfer assets all the time. You can actually digitally write some info on the blockchain, okay? Yes, let's move on to digital signatures. For this reason, we need to talk about public key cryptography, or with a different name, asymmetric key cryptography. Asymmetric key cryptography provides the ability to verify that the user transferring value to another user is in possession of the private key capable of signing the transaction. Private keys are used to digitally sign transactions. Public keys are used to derive addresses. Public keys are used to verify signatures generated with private keys. So idea is simple. Whenever you use a cryptocurrency or a blockchain, you generally create a private key and the corresponding public key. This is done generally by your wallet software automatically, okay? So whenever you sign a transaction, actually you use your private key. And for instance, in Bitcoin, you derive your address from your public key, which is actually hash of this public key. So whenever somebody wants to send money to you, they actually send it to your public key, and you don't have to be online for this, okay? They just sign a transaction saying that the new owner of this cryptocurrencies have this public key address. That's it. So whenever you want to transfer it to somebody else, you have to, now sign a transaction with the private key that belongs to this public key. And whenever you do that, every node actually verifies the signature by using your public key. Okay, this is how you actually prove that you really own that, and now you are transferring it to somebody else. Okay. Some permission blockchain networks can leverage a business's existing public key infrastructure for asymmetric key cryptography to provide user credentials, rather than having each blockchain network user manage their own asymmetric keys. So assume that, for instance, you are using PGP, everybody already has some public and private keys, so you can simply continue using them on the blockchain. That is what it's trying to say, actually. This is done by utilizing existing directory services and using that information within the blockchain network. Blockchain networks which utilize an existing directory service can access it via existing protocols, such as the lightweight directory access protocol, and utilize the information from the directory natively, or import it into an internal certificate authority within the blockchain network. So as you can see, people are very familiar with permissionless blockchains due to Bitcoin and Ethereum. So there you simply create your private and public keys by simply pressing a button on your wallet software. But you might lose this information and so on. But if you already have an existing asymmetric key services, you can integrate it into your blockchain in a permission blockchain, because now since you already know who the people are, so you can give them authorization this way. So you don't have to always use the idea of the Bitcoin, okay? You have some other ideas, because all you need is a public and private key for everybody, right? So if you already have in a different service, then you can use it. Yes, digital wallets. This is important because people say that digital wallets are digital analog of physical wallets, right? So hence the name. But let's look at what physical wallets do. So they have three main purposes. You store cash on it, right? And when you remove cash from it when you pay cash. And when somebody gives you some money, you put it there, right? You receive the cash. So it stores, gives and receives, right? So they say that many books, blogs, web pages claim that digital wallets are digital analog of physical wallets and are used to store cryptocurrency, send cryptocurrency, and receive cryptocurrency. So this cannot be any more wrong. And this is very important because this actually forces people to think that they have their cryptocurrencies, NFTs, any digital assets on the wallet software, which is on their laptop. So they think that everything's stored on the laptop, okay? But they are stored in the blockchain. That is important. None of your cryptocurrencies, NFTs are on your laptop. They are on the blockchain. And also not the NFT themselves, but the link that is mapping the images or the videos which we'll talk about. So this is important because a lot of forensics people couldn't understand this for a very long time. So for instance, when a person admits that there are cryptocurrency on their laptop, forensics people think that if we don't connect it into internet, it cannot leave the laptop, so it stays there. But if somebody has the private key of that account, they can easily transfer it to somebody else, okay? So this is very important. Digital wallets do not store cryptocurrency. They store your private keys and public keys. That's it. With some blockchain networks, users must manage and securely store their own private keys. This is important. You have to store it in a secure way. If it is not secured, if you have a Trojan in your system, somebody might get your private keys and, claim everything in your account. And it is also important because, for instance, if you're keeping it on your laptop, only there, and if it is broken, if your hard drive is broken, you lose it. And there's no way of returning it back. Recall that we talk about discrete logarithm problem. And here you have to solve elliptic curve discrete logarithm problem to, recover your private key. If you can do that, this means that you can obtain every private key of everybody. So you can, capture every cryptocurrency. But if you can solve that problem, maybe you wouldn't bother with cryptocurrencies and break every computer system connected to internet and listen to, everybody's communications, withdraw money from any bank and so on. So this is why it is important that that problem is hard to solve. Okay. They often use software to securely store them. And if you use in practice, most probably you will see in the Bitcoin, for instance, you create your private key. So it is simply a file on your laptop. But again, if there is a Trojan, they can get that file. So what software generally asks you to choose a password. So you choose a password. They put that password as an input to a hash function like SHA-256. They obtain the output, but they put it as an input again and do this for thousands of times. And at the end, from your password, you obtain 256 with output, right? So they use AES 256 to encrypt that file on your computer. So this is why most of the time your private key is stored in your hard drive in an encrypted way. This is important for forensics people. So if you want to decrypt it, you have to capture the password. So this is why you need to choose a good password. Okay. So for this reason, if you do this, use the system, whenever you want to make a transaction with your wallet, the wallet will ask you to enter your password. Because when you enter your password, it recreates your encryption key, decrypts this private key file, and uses it to make the sign the transaction. This is how encryption actually only involved in my course right now. But again, I'm not using it on the blockchain. I'm using it to encrypt a file on my computer. That's it. Yes. So there are other ways of doing it. Of course, you can simply choose a password, or sometimes they give you like 20 words in some specific order. And if you write them again in that specific order, you recreate your password. Those are similar ideas, but maybe they can be used in different ways. For instance, maybe they are using that data to create your private key. Because recall that in the elliptic curve digital signature, we use the number D, which you randomly choose, and that is your private key, right? So in my example, I show you how to encrypt it. Maybe some wallet software give you some data which would only use to derive that private key. That is a different thing, okay? You have to check the white paper and see what they are doing, okay? Because in my scenario, you have to have the encrypted file in your hard drive anyway. If you lose that file, knowing that password would not benefit you, right? You are losing the file. But in most of the wallet software, you use those words. But even if, you know, if only those words are used to derive the private key, even if you lose every file on your computer, you can go to another system, write those words in that order, and recover back your private key, okay? Those are two different things. I don't know if I could explain this clearly, but in one case, you create the private key, then encrypt it with a password. In the other one, you create the private key from those words. Okay, those are two different things. And we will talk more about them when we talk about Bitcoin and Ethereum. Okay, this software is often referred to as a wallet. The wallet can store private public keys and associated addresses. This is the important part. As you can see, the wallet stores this kind of data, not your cryptocurrency. But since they know your public keys, they look at the blockchain, search for your public keys, and then show you how much cryptocurrency you have. It may also perform other functions, such as calculating the total number of digital assets a user may have. If a user loses a private key, then any digital asset associated with that key is lost because it is computationally infeasible to regenerate the same private key if you don't have a trapdoor. And in those cases, those 20 words, you have generally a trapdoor for that. Let's move on to ledgers. Distributed ownership of ledgers versus centralized ownership. So this is the part where you can ask, why don't I use a bank but a blockchain, right? Because banks have centralized ledgers, and here we are talking about distributed ownership of ledgers. So question is, why would we use distributed case, right? Because the main question is, do you trust your bank? Okay. Centrally owned ledgers may be lost or destroyed. I mean, generally, it is not the case for the banks, right? But for some other scenarios, this happens. For instance, some companies store your database in a building and have the backup in the next building. But if an earthquake destroys both of those buildings, you lose your data. This is why having a distributed database is sometimes preferred. And in some cases, some of the companies actually became bankrupt after this kind of natural disasters. Standalone ledgers may be on a homogeneous network. Here, the idea is saying that they have to be somewhat using the same system, same hardware, same operating system, so that they have the same data. But in the distributed, I mean, think about Bitcoin. I can install it on my laptop, so I'm using a different CPU, different hardware, and so on. So we have more flexibility. Centrally owned ledgers may be located in a specific location. This is why a natural disaster or war, like the case in Ukraine, might affect this kind of situation. And currently, there are some parts of Ukraine where you don't transfer money physically, but instead use a stable coin, because it is hard to transfer huge amounts of money in a war zone, right? The transactions on a central owned ledger are not made transparently and may not be valid. This is actually something we never considered, but maybe, for instance, I tried to send you money, but didn't tell you, and you didn't receive it for some reason. So you would never know, right? Because things are never transparent. And you have to go to your bank and say that my friend sent me money, and in some cases, here it is, we didn't notice it for some reason. There are some examples for this. So it is not transparent. So what I'm trying to tell you is as follows. When you create a Swift operation, for instance, it takes days, and the person who is going to receive it doesn't know that they are going to receive that money. But in the cryptocurrencies, whenever I announce a transaction, everybody hears it. So you know that, okay, he really is trying to send me the money, but we have to wait it to be written on the blockchain and so on. So this is why transparency is somewhat important. The transaction list on a centrally owned ledger may not be complete. The transaction data on a centrally owned ledger may have been altered. This is always the paranoia of people. People always wonder if some bank personnel is taking their cents without their knowing it, because you never check that, right? So if this happens, you would never notice most of the time. But of course, here I'm talking about, of course, trust issues. If you trust your bank, there's no problem. Of course, don't think of this always as bank versus cryptocurrency. Here we're talking about centralized ownership of a ledger with a distributed ownership of ledger. What you are storing on the ledger depends on the scenario. Okay. I'm trying to just justify why we use cryptocurrencies. The standalone system may be insecure. A user must trust that the associated computer systems and networks are receiving critical security patches and have implemented best practices for security. The system may be breached and have had personal information stolen because of insecurities. So there are many examples for that. I'm not going to name it, but when I was doing PhD in Switzerland, there was a bank there, and some personnel, turn their computer on and go home at the weekend so that they can work remotely. But there was a virus in this computer, so they actually withdrew millions of francs without people noticing it. This kind of things can happen. This is why it is hard to provide security for all of the computers in a bank. This is what we are trying to tell. Blockchain network users submit candidate transactions to the blockchain network via software. So your wallet software actually does this, and you write that I want to transfer this amount of money, this cryptocurrency. You actually create a transaction. For many blockchain implementations, once a pending transaction has been distributed to nodes, it must then wait in a queue until it is added to the blockchain by a publishing node. So this takes some time in permissionless networks, but if it is permissioned, you can write it directly because you have the authority. Transactions are added to the blockchain when a publishing node publishes a block. The block header contains metadata for this block. The block data contains a list of validated and authentic transactions which have been submitted to the blockchain network. Okay, these are what is stored in blocks. Validity and authenticity is ensured by checking that the transaction is correctly formatted and that the providers of digital assets in each transaction have each cryptographically signed the transaction. So this is important. So this is what happens in the background. Whenever you create a transaction, actually the nodes check the signatures for every input that is inside in your transaction. So this is important because traditionally, when we say transaction in the banking system, you're actually moving some amount of money from an account to another account, right? But in cryptocurrencies, a transaction may include multiple input and multiple output from different accounts. So you have to check signatures for all of these to verify that transaction. This verifies that the providers of digital assets for a transaction had access to the private key which could sign over the available digital assets. The other full nodes will check the validity and authenticity of all transactions in a published block and will not accept a block if it contains invalid transactions. Okay. So the security comes from digital signatures, in other words. Many blockchain implementations utilize data fields like the following: block header, which contains the block number, also known as block height, previous block header's hash value, a hash representation of the block data, methods like generating a Merkle tree and storing the root hash, or by utilizing a hash of all the combined block data can be used. So it is up to you. But in the Bitcoin, you use a Merkle tree. A timestamp, the size of the block, the nonce value. For blockchain networks which utilize mining, this is a number which is manipulated by the publishing node to solve the hash puzzle. In Bitcoin, this is 32 bits, and it is not enough to actually solve the problem. You can try every 2 to the 32 nonce value, and most probably you will not solve the mining problem. So you should go to the transaction data and modify it, then modify the nonce again and again. We will talk about it when we talk about Bitcoin. Yes, the header contains this data, and you have the block data, which generally is a list of transactions and ledger events included within the block. Other data may be present depending on how you create the actual blockchain. So here's a simple picture from the NIST report, Blockchain Technology Overview. So you have the block header here and your block data here. This data is, again, the transactions and so on. So here you have previous block headers hash, timestamp nodes, and hash of the block. So whenever somebody, for instance, in the case of Bitcoin, solves the hashing puzzle, obtains a hash value, right, starting with many zeros. So it becomes this part of your next block. So you write it here and wait other transaction data to be heard. You solve the mining problem again using the nodes and so on, and go it and so on and so forth. This is why if you change anything here, this also modifies the also hash of the block data, but this value too, right? So this is why going back and modifying a transaction is not easy, because changing this changes everything. So it creates actually another block. So here you can, in the timeline, you can create a parallel universe and try to, create blocks faster than this one and, go in front of them. So if you can create something larger, longer, that will be your new Bitcoin blockchain, and these ones will be discarded, will be orphaned. But in order to do that, create a parallel universe and solve the mining puzzle faster than this one means that you have at least 51% of the mining power, and this way you can actually perform the attack. So Bitcoin has never received such an attack, but many cryptocurrencies seen this kind of attack in the past. Okay. So this concludes our discussion of blocks.